In this video I want to address the following question. Why do many stochastic processes showcase a Gaussian distribution? I want to give you a mathematical answer without showing you all the steps. If we consider a stochastic process and we associate that process with the signal x of t, we can expand that signal into a Fourier series. This is a Fourier series, the expression for a Fourier series. Let's focus on the amplitudes of the sinusoids here, of these cosines, a sub n, and the frequencies of the sinusoids and also the phases of these sinusoids. We will see that the phases and the amplitudes are very important for providing the answer to the initial question. Now let's define moments. And in particular here you see the formula for moments, mq, where q is an integer which ranges from 0 to infinity, and it consists in calculating the following integral here. We have to integrate the function x of t in this manner. We subtract c0. What do I mean by c0? c0 is just the average of the function x of t. Then we raise that to the power q and we integrate it over the period t. The period t is the period where we expand the function x of t in a Fourier series. So if we expand the function in a Fourier series, we associate that function with a period, and this period here is capital T. I will not get into the technical details. I have created a course on this where I show you all the mathematical steps, but here I just want to show you the main results. Then if we integrate the signal x of t given by this formula here, it can be shown that the result is the following. It is quite a complicated result, as you can see, because the formula is not so easy to understand at first sight. But it's not too complicated either. I want to direct your attention towards the amplitudes and the phases of the signal. So the amplitudes and the phases of the signal, you can see that they enter into this formula. They affect the qth moment of the signal x of t. And then I also need to introduce you to a different formula which can be proved. The formula is this. The probability density function p of x can be written in this kind of complicated way. It has to do with the Fourier transform, but you can see that a probability density function can be reconstructed if we have the moments mq of a stochastic process, because mq is in the formula, as you can see. If we replace this particular formula here under certain assumptions, such as the fact that the phases of the stochastic process are associated with the uniform random distribution, it is possible to prove that this formula will yield this one, and this is the famous Gaussian probability density function. Therefore, the stochastic process is associated with a Gaussian distribution. I have created a course which shows you step by step how to prove all these facts. In this video, I just wanted to give you an overall overview of the main results, which are very important in natural processes because we often witness Gaussian distributions in nature. They are not the only kind of distributions, of course. That's not what I mean. But I mean that this is a very important distribution because it appears very often.